Hello everyone, welcome back to our lecture on soils. So we're going to continue talking about soil textures. So soil texture is the distribution of different grain size particles within a soil. So it is the composition of clay, silt, and sand within the soil. So clay is any sediment that has a grain size diameter of less than 0.002 millimeters. And then silt is anything above that up to 0.0625 millimeters. And then sand is larger than that, up to 2 millimeters across. And so you can see here the different maps of the distribution of clay, silt, and sand. You can see, for example, sand dunes in this region and heavily sandy soils in Florida with all those beaches. And then you can see the Pine Barrens too in New Jersey that have highly sandy soils. And so we use this useful chart to classify different soil textures based off of their composition of sand, silt, and clay. For example, if a soil had 40% sand, we can go up this chart to 40 and then go across, and we see that it also has 40% silt and then 20% clay. Then that soil would be a loam. And you can use this chart to figure out for any percentage of sand, clay, or silt what the resulting texture name would be. So the soil texture has a big impact on the erodibility. You can see here that clay rich soils tend to have very erodible soils, whereas more sandy soils are harder to erode just because those larger particles require more energy to move. But also it has an effect on hydraulic conductivity, and there's some interesting features that come out of this chart. Generally, when you have more sandy soils, sand has more pore spaces, and so water can flow through it more easily. And so the more sandy the soil, you can have hydraulic conductivities on the orders of 5 or more inches per hour. But also you'll see that there's some strange features here as well. For example, the middle of the chart that has roughly equal percentages of clay, silt, and sand has an anomalously low value for hydraulic conductivity. And that's because when you have a large grain size distribution, many particles of different sizes, then the smaller particles tend to fill in the spaces between the larger particles, and the void space is decreased, and the porosity decreases when you increase your grain size distribution. Whereas, for example, here where you have no sand and it's just made up of silts and clays in equal proportion, then the hydraulic conductivity is higher because you don't have those void spaces being filled as easily. So next we're going to talk about soil orders. So soil orders is a way of classifying different soils based off of their properties. And there's 12 different soil orders that we'll talk about. And you can use this nifty schematic in order to classify a soil into its different order. The first soil order is a gelisol. So these are permafrost soils that we've talked about previously in this class, and we'll talk about more further on. But it's soil that has ice in it, and usually has some sort of cryoturbation, such as the ice lensing that we talked about previously. And so gelisols can cover wide swaths of the Arctic, and so they cover about 9% of the land surface Next, we have histosols. So these are highly organic matter rich soils. They can occur in places like peat marshes or very mucky bogs or areas like that, where you have extensive organic matter develop. You have highly fertile soils with a lot of water available, and so you can form these very thick, very dark in color soils that are histosols. Next, we have spodosols. So spodosols are highly acidic soils. You can have weathering processes that strip away the organic matter along with the aluminum in the soil, and it leaves very prominent E horizons that we talked about just previously. And so you can see here, for example, that this soil has a low acidity. And so spodosols cover about 4% of the planet and tend to have coarse textures associated with them, and they tend to be in areas with extensive decomposition, such as in forests or more humid regions. So the main feature of spodosols is that high acidity. And then next we have andesols. So andesols are formed from volcanic ash. So you may have heard that after a volcano erupts, the soil that results after all the destruction has cleared is highly fertile. And that's because volcanoes produce a lot of volcanic glass, which is a quickly cooled solid rock that doesn't actually form crystals, and so it easily erodes and can easily be converted to nutrients by plants and organisms in the soil, and therefore it tends to be very productive soil. And it covers only about 1% of the Earth's surface, though. And so next we have oxisols. So oxisols cover about 8% of the Earth's surface, so fairly large area. And oxisols have been intensely weathered, usually in tropical or subtropical regions. So you have a lot of clay minerals, such as kaolinite, develop, and iron oxides. And so a lot of the water that flows through these allows the soil to break down readily, and you don't have as much distinctive soil horizons because everything is being weathered so quickly. Next, we have vertisols. So vertisols are very cool soils, and they cover about 2% of the Earth's land surface. And so vertisols swell and shrink depending on their water content. So they have heavy concentrations of clay minerals, and clay minerals like to absorb water very readily. And so as you have more water seeping into cracks, that soil will actually expand and absorb that soil moisture. And so they're generally fairly high fertility as well, because those clay minerals can give off their nutrients fairly easily. Next, we have aridosols. So these are desert soils. These are soils in very arid, dry climates. And as a result, they don't have their particles weathered very well. And so you have a lot of rocks and large material in that soil. You can also get a lot of salt and calcium carbonates that we talked about previously, because you don't have that water moving through the soil and dissolving it away. And so deserts are fairly common on Earth, and so aridosols cover about 12% of the land surface. Next, we have altisols. Altisols are soils that have experienced extensive leaching, and so they're usually soils in humid areas, and that humidity allows the nutrients to leach away from it. And so you have typically acidic soils where the organic matter is just concentrated in the upper part and doesn't go very far down. And so the altisols generally have low base saturations and heavy clay substrates. Next, we have grassland soils or mollisols. So mollisols cover about 7% of the Earth's surface. And these are soils that you see in grasslands. So they tend to be fairly organic rich because the grass can grow its roots deep into the soil and decompose and form well-developed soil horizons. And so you can see here that organic matter going down pretty far into the soil and developing a very healthy soil as a result. Next, we have alpha sols. So alpha sols are soils that have been moderately leached but have very fairly high moisture contents. And so alpha sols are known for very well-developed E horizons. And you can see that here, that E horizon that's developing under the topsoil. And so that's just because it's been heavily leached and it has a lot of water in it. So you have a lot of clay minerals that develop and get leached out. Those are alpha sols. Next, we have inceptisols. So inceptisols are baby soils. So inceptisols cover about 17% of the world's area, and they're just recently developed soils, usually in semi-arid to humid environments, where you still have predominantly a sea horizon with a lot of boulders and not well-developed soil, and then it's just kind of starting off, making a more developed soil. And then lastly, we have entisols, which is kind of the catch-all for a soil that has pretty much no soil horizons. It can be just a big old pile of sand would be an entisol because it hasn't really developed much. It doesn't have all that much organic content and is usually just recently deposited next to its parent material. And so, for example, a sand dune or a river floodplain would be an entisol, and these can cover a large area of the planet, 16%, because there's a lot of area that doesn't have has either steep slopes or sand dunes or river floodplains that entisols are characterized as. All right, so those are soil orders. And you can see a map of the distribution of these soil orders here. For example, we have those gelisols, the permafrost soils in the Arctic here, as well as inceptisols, where those baby soils that develop in more mountainous regions, such as in Alaska, and aridosols, for example, in in the Sahara region, as well as in Saudi Arabia, for example. So those you can see how different climates might affect the soil type that's present there. So next we're going to talk about how soils and climate change are interlinked. So soils, as we've talked about, have a lot of organic carbon in them. And if the soil degrades, that carbon can be released into the atmosphere, which can further exacerbate climate change. So keeping a keen eye on soil health is really important for monitoring the effects of climate change. So there are a number of different processes that can either degrade or restore a soil. For example, monocropping or heavily compacting soil or extensive tillage or use of chemical fertilizers tend to degrade a soil, whereas other processes mostly relating to leaving the soil be, tend to restore the soil, such as reducing the amount of tillage, reducing the amount of contamination, and allowing for biodiversity. So we can see here, this is the soil carbon stock of topsoil throughout the planet. And what's notable is that the carbon stock is highest in the Arctic. So you have a lot of carbon that's stored up in permafrost. And so if that's to melt, then that carbon can be released. And so as a result, the warming that we've already seen due to climate change and global warming has been responsible for 10% of all greenhouse gas emissions. So changes in land use, as well as warming of permafrost, has resulted in 10% of the gases that have been emitted due to anthropogenic climate change. So this is definitely not insignificant. And we can see here a map of those carbon emissions from soil, with the vast majority of carbon emissions coming from the Arctic. As you melt more permafrost, that permafrost melts, and the carbon can now start to be broken down and will be released into the atmosphere. And some areas of the Arctic have experienced several 10 to 20 kilograms of carbon being released for every cubic meter or square meter. So that's definitely not an insignificant amount. So we can use climate models in order to predict how much stress the soil will experience in the future. So depending on our emissions scenario, the amount of soil moisture is going to change. So you can see here with a RCP 2.6 scenario, that's the rapidly addressing climate change scenario, you don't have all that much change in soil moisture. Whereas as you get to higher and higher emission scenario, up to the RCP 8.5, which is the business as usual scenario, you have very drastic changes and decreases in soil moisture throughout Europe, South America, the United States, and South Africa. And so that would have tremendous impacts on soil fertility and crop yields. Additionally, the soil temperature is expected to further increase, and so the difference between the business as usual scenario and the Paris Climate Agreement 2 degrees Celsius warming, which is the RCP 4.5 scenario, really starts to become prominent after 2060, where the temperature of permafrost soils is expected to be over 2 degrees warmer in a business as usual scenario. And when you have wide swaths of permafrost land that are right close to freezing temperature, then 2 degrees warming, because we're not reducing our carbon emissions, is really significant. And you can have huge amounts of landscape that's now being exposed to warming. As a result, crop yields will likely decrease as a result of climate change. As soil becomes less fertile, has less organic matter in it, and has lower water content, then it can produce less crops. And you can see that here, that under a business as usual scenario, corn will likely decrease its yield by 50%. And you can only imagine how many farmers would be able to maintain their business if their crop yield was to drop by 50%. It would be extremely traumatic to large populations in the United States, and it would greatly increase food costs. Additionally, other crops such as soybeans, wheat, and cotton have drastically different crop yields depending on our emission scenario. And so a business as usual scenario would likely cause the cost of clothing to go up as well as cotton becomes less available. So the reachings of climate change are extensive, even in soil science. So we have to be very vigilant to making sure that we're not going down a path to these more dramatic results. So that just about covers it for our lecture on soils. In summary, we covered soil composition, soil horizons, soil color and what that means for the soil chemistry. We talked about soil pH and how that affects nutrient availability. We talked about soil textures and how to classify soil textures. We talked about the 12 different soil orders. And then we just talked about the impacts of climate change on soils. So thank you all for watching. Hope you enjoyed the lectures for this week, and I will see you next time.